So our next topic we're going to look at is we're still dealing with limits, but now we're going to approach it from a graphical perspective today. We've kind of done that a little bit already with the algebra. We've thought about a limit as being either a y-intercept or a point of discontinuity or an asymptote or something along those lines. But we're going to look a little bit deeper at graphs and see if we can figure out limits from a graphing perspective without having to do the algebra. So our first topic that we're going to look at is just sort of let's do a quick review of what we've already done. So this first one that I've got shows a cubic equation divided by a linear. So let's kind of go through our steps again as a review. First thing, plug in the value. So if we plug a 3 in, we would get 3 cubed minus 27 over 3 minus 3. Well, 3 cubed is 27, so that's going to give us 0 over 0. So remember, this is typically going to be our situation where we're going to get a point of discontinuity. So if let's do it from algebra first, and then we'll kind of connect it to the graph. So if you remember from algebraically, in this case, a good strategy is to do the factoring. So if we factor the top, remember with cubic factoring, we would get x minus, like cube root both of them. So cube root of x cubed is x, cube root of 27 is 3. And then the leftovers was the first one squared. And then the next one's multiplied. So 3 times x, and we have to make it plus. And then our last one was squared as well. So that should be our simplified factors on the top. And you can see our x minus 3's would cancel, that's the one that's causing us the problem. So now we should be good to go. If we do our limit as x approaches 3 of x squared plus 3x plus 9, that should give us 9 plus 9 plus 9, which is 27. So what we figured out is that when x is 3, we're getting a y value of 27, and that should be our point of discontinuity. So from a algebra perspective, that's what we've just determined. So at the coordinate 3, we have a point of discontinuity of 27. So remember, a limit isn't telling us what the coordinate is or where it should be, it's just saying what is x approaching. So let's look at this from a graphing perspective now. So if we graphed either our original equation or we graph our simplified version, they should be almost identical graphs. So if you put those in on your calculator, we end up getting a quadratic kind of graph that looks something like that. So what we're seeing is it's a continuous function almost everywhere except at the coordinate 327. So way up here, we got some sort of point of discontinuity. So the hard part is, if you were to do this on your calculator graphically, is you might not, well, you won't see it. You won't see that point of discontinuity on your calculator. But if we went to your table or something like that, it would say 3 undefined on the original graph. On the simplified graph, we would get the coordinate 327. So the idea is, if we look at it from a graphing perspective, is could we figure out what that limit is? The answer is yes. It's going to be the coordinate that we're approaching as we get closer and closer to x equals 3. So our next issue is going to be, well, what happens when we examine this a little bit further? So on your calculator, like I said, you can't really see it, but we could try a few different strategies. So here's our same one. I just wanted to make it a little bit better of a picture. So on your calculator, if you were to graph this out, our quadratic would be, again, something like that. So if we went over in your calculator and we found that coordinate, let's suppose it was way up here somewhere, my graph isn't very accurate, but close enough. If we found that coordinate was at 327, we'd have to be able to see it from a graphing perspective. So your regular calculators, you can't see it. If you went to your table, remember the table's not bad, it would tell you 3 and undefined or error or something like that. So that helps. But a good feature to do on your calculators, if you're not sure, is to use trace. So if you put this in on your calculator and just trace and move your cursor over to 3 and just kind of go on either side of 3, you should be able to estimate that our answer would be 27. So trace value works quite well, and it's something that you can always explore graphically. So we're going to look at our limit laws now from a graphing perspective. And what we say is, if we look at a graph from the left, so if we're drawing it from left to right, we call the left-hand limit as what that graph is approaching. So let me kind of go back to that one that we just had. So we knew that we had at 327, we had a point of discontinuity. So when we're saying what the left-hand limit is we're saying what is x approaching, or what's, as we approach x from the left-hand side, or from the, in this case, below the 3 value, what's the y approaching? So how we'd actually write this one is we'd say the limit as x approaches 3 from the left, or for the numbers that are less than 3, so we write it as 3 with a little minus sign up top. Let me fix that up a little bit. So we'd write it as x approaches 3 with a little negative. So that's showing us the left portion of the graph. So in this case, as we get closer and closer to 3, our limit was 27. We're getting closer and closer to 27. So now from a graphing perspective, we do the same thing from the other side. So if we approach it from the right-hand side, we want to figure out what that limit is. So in this case, if we did our limit as x approaches 3 from the positive side, or for the numbers that are just a little bit bigger than 3, we're also getting 27. So we're getting kind of a matching limit from both sides, and that's what this limit law is saying. It's saying that if our two limits from the left and the right are indeed the same, then we will actually have a limit. If they were different, then we don't. So like I was just saying, for any general function then, if our left-hand limit, which is this x approaches a from the negative side, equals our right-hand limit, if they're both equal to each other, and that's the key thing, if they're equal to each other, then that limit is exactly that. So in the one that we just had, we had limit as x approaches 3 from the left was equal to 27. We had the limit as x approaches 3 from the right. That was also equal to 27. Because 27 is the same for both, then our overall limit as x approaches 3, we would just say, is indeed 27. So we sort of have to look at it from the left and the right and see if they match or not. If they don't match, then we just simply say there's no limit. So for example, let's suppose for that last graph, if I said x approaches 3 from the left and we got an answer of 2, and we did x approaches 3 from the right-hand side, we got, let me fix that plus a little bit. So if we approach 3, but from the right-hand side, so that'd be 3 with a little plus up top. And let's suppose that answer was 4, because 2 doesn't equal 4, then we would just say no limit in this case. So this is where, if you're going to use your calculator, the trace feature works pretty good. You'd see it as you approach from one side, of getting closer and closer to a certain number, approach from the other side. If those numbers match, you're in business. So what typically happens when they don't equal the same thing is we usually get a break in the graph, or like a little jump or step in the graph. So that's what we'll explore next. So for when a graph is continuous or not continuous, this is usually where the left-hand limit and right-hand limit things come in to help us out a little bit. So you can see for this rational graph I've got on the equation, it says our equation was 1 over x minus 1. So if we're trying to determine the limit as x approaches 1 for 1 over x minus 1, if we plug that in, we get 1 divided by 0, which basically we said earlier was no limit. So let's explore that from a graphing perspective. If we look at this graph and we figure out what's the limit as x approaches 1 from the left side, so that means we're going to get closer and closer to 1. So you can see our graph is getting smaller and smaller, so that limit would be negative infinity. If we figure out the limit from the right side, we follow the graph, you can see in this case it's getting larger and larger, so that's approaching positive infinity. Since negative infinity doesn't equal positive infinity, that meant that we have no limit. Okay, so algebraically, that's where we had like a 1 divided by 0 scenario. Graphically, you can see what's going on. So generally in these cases, if we get a number divided by 0, you can see what's happening is we're dealing with vertical asymptotes. So we've sort of looked at 4 possible cases. So if we, for this question, if we would have done what x approaches when it's 2 or something like that, we would have just got a number. So that would have been our y coordinate. We looked at scenarios where we had 0 over 0, which was a point of discontinuity. Now we have 1 divided by 0, which is giving us our vertical asymptote. And then we also looked at when x approaches infinity, gave us our horizontal asymptote. So we're kind of covering all of the different possible locations or features of a graph. So let's look at this next one. So you can see that our function was 2 over x squared minus x. And if we factor it, might make it a little bit easier to see. So we have 2 over x and x minus 1. So from Math 20 or Math 30, we would know that we have asymptote lines at 0 and 1. So you can see the way the graph shows below. We've got a vertical asymptote right at 0. We've got a vertical asymptote at x equals 1. So at those locations, we should have no limits. And if we kind of look at it from a left and right hand point of view, on this, as x approaches 0 on the left, it's approaching positive infinity. On the right, it's approaching negative infinity. So that one has no limit. And the same thing for the other one. From the left, it's negative infinity. From the right, it's positive infinity. Also, no limit. So at both of those two locations, if the question was saying what are the limit as x approaches 0 or the limit as x approaches 1, we would say for both of them no limit or does not exist. Okay, and you can see graphically that's telling us that we have a vertical asymptote. So it kind of ties everything that you already learned together and connecting it with the limits as well. So the hardest kind of graphing questions aren't generally just normal functions that you put on your calculator. We usually deal with piecewise, and these are the ones you're not going to typically use your calculator for. You're just going to sort of sketch out what the piecewise would look like, and I guess you could use your calculator to get each section, but once you have it sketched out, just by looking at the graph, you'd be able to figure out the limits a lot easier. So for example, if we look at this picture that I've got on here, we've got 3 different functions. We've got a y equals x squared. So if I was to, let's see if we can remember how we would write these out. We would say we have y equals x squared, and you can see that that graph is from everything from below 2. Right? Like if we look at our coordinates here, we'll just assume they're 1s, which I think they are. We'd have a y equals x squared graph if x is less than 2. So let's do this in interval notation. So that'd be from negative infinity to 2. Okay, you can see the middle one is just a dot, so that's just telling us y equals 6 if x is just equal to 6. Or sorry, just equal to 2. So when our x value is equal to 2, we get y equals 6. And then you can see our third line on there is y equals 10 minus x. So it's just a linear line. And it's saying that's occurring when x is equal to 2, or not equal to 2, but greater than 2, up to 3, 4, 5, 6, it looks like. So from 2 to 6, we get that linear line. So that would be our 3 functions. So you could graph those on your calculator if you really wanted to, but it's probably easier just to sort of sketch them out by hand. So now what's happening is we've got some weird limits going on. So if I was to pick just some sort of continuous location, let's suppose I said what's the limit as x approaches negative 1, we could just look on the graph and see when x is negative 1. That's just a normal coordinate. That one would be 1. Or if I said what's the limit as x approaches 4. So again, look on your graph, figure out where 4 is. We can see 4 is just another nice location, and that's going to be 1, 2, 3, 4, 5, 6, it looks like. So those are just our y locations, so those are pretty easy. The only case on this graph that's going to be an issue is what's the limit as x approaches 2. So if I just ask what is f of 2, whether we use the equation or we use the graph, f of 2 is that solid dot on the graph, which is at 6. So f of 2 is 6, but the limit of 2 isn't 6 in this case, because we have to do our left and right hand thing. So if we did limit of 2 from the left, so that means we're following this graph going upwards, that one's at 1, 2, 3, 4. Right? So that limit would be 4. But if we do the limit as x approaches 2 from the right, that's on the other graph, so now we're following this line, that limit is approaching 8. 4 doesn't equal 8, therefore the actual limit as x approaches 2, the overall limit as x approaches 2, doesn't exist. There's no limit. So the graph, when you look at a graph, anytime you see these breaks in the graphs or sort of steps or separations, often there's going to be no limit. It only would matter when these limits are both approaching the same thing. So let's try, I'll just draw kind of some random piecewise functions, and let's just try a couple more. So let's suppose we had, let's say it was some sort of curve, let's do a quadratic, and let's suppose it went to this point, and we'll do an open dot there. Let's say it carried on forever in that direction. Then let's suppose from that open dot it jumped up and made just sort of a linear line. Let's say it was a closed dot there. And then let's say from that closed dot the graph jumped down. Let's say it's an open dot here, and it did some other kind of quadratic type shape like that. Okay, so you can see we sort of have three different functions. And again, I don't care really what the equations are, let's just look at the limits. So for the first one, let's try to figure out what the limit is as x approaches -3. Okay, so we're looking for this -3 location, which is right there. So if we do it from the left side, so if I say limit as x approaches -3 from the left, so that means we're following this bottom part of the curve. You can see as it gets closer and closer, our y value is approaching 0. If we do the limit as x approaches -3 from the right hand side, it's also approaching 0. Since those two are the same, then our overall limit is indeed 0. So you kind of have to just look at the graph and see what is approaching on either side. And it wouldn't matter if this was an open dot or a closed dot, they're both going to be approaching 0. Even if there was a different dot somewhere else, like let's suppose we had an actual solid dot up here somewhere. So if f of -3 was 6, the way I drew it, that's our coordinate, -3, 6, that's the actual location of the graph, but that's not the limit. The limit is where are the lines approaching. So ignore those extra dots, just look at the curves and do the left and right hand thing from there. So let's do the same thing for the second one. Let's try to figure out what is the limit as x approaches 5. So if we do the left-hand limit, it's approaching the value 10. So limit as x approaches 5 from the left, we can see it's going to 10. If we do the right-hand limit, as it approaches 5 from the left, or from the right, we're approaching the value 5. Since 10 does not equal to 5, we actually have no limit at that location. And you can see just by looking at the graph, there's a break in the graph, right? So these two points aren't approaching the same thing. Therefore it's no limit. These two were approaching the same dot, those ones weren't. So graphically it's pretty easy to pick out what the limits are. And that's where we'll stop for now.